Hello and welcome to a new video. This is for Algebra 1. We're still talking about systems of equations, but in this lesson we're going to talk about how do we choose a method whenever we get to choose, and also we're going to talk about the special cases that can happen. So I have here Choose Wisely, which is actually an Avatar: The Last Airbender reference. If you haven't seen that show, it's probably one of the best shows of all time. But it's whenever Boomy goes, choose wisely, and then Aang chooses, and then he's like, wrong choice. So we don't have high stakes here for choosing. The worst that can happen is that it wasn't the easiest method. But we're going to talk about here at the beginning, like, how do we decide? How do we pick what is probably going to be the easiest method? So let's see. Here's our three methods: graphing, substitution, and elimination. Graphing is, I would argue, the easiest method or the fastest method, but only in certain circumstances. There are actually a lot of circumstances where it's not going to be the easiest or fastest. So it's definitely the one that it's like, hey, this is the one we almost don't really need to talk about, but it is what shows us what's actually happening, right? That when we solve any of these systems, what we're talking about is two lines and where they intersect. And it's also just, if it happens to work out that they're in slope-intercept form and you have some graph paper handy, then it's probably going to be the easiest way to go. So that's what I would say here about graphing is I would choose graphing if the equations are in slope-intercept form and I have graph paper handy. Or I guess or would also work. Because if you're like, oh, I think I can solve this for y, anything can be graphed, right? And graph paper. I should have put and you have graph paper, and graph paper is nearby. Just a hop, skip, and a jump away. We have graph paper. Okay, substitution. Substitution, I would say, is the easiest method to use, or the method that I would go with to use if one of our equations is already solved for a variable. Because if it's already solved for a variable, then we'll have to do work to get it set up for elimination. So I'd say if one of the equations is solved for a variable, so solve for x or y, the other thing that would make me want to use substitution is if the numbers just don't seem like they'll work out for elimination. So if the numbers don't seem easy to find a least common multiple of, basically. To find a LCM, un-LCM, whatever. I'm going to be honest. Elimination is my favorite of the methods. I think it's the one that works best the majority of the time, particularly if they're both in standard form, which is where you have x plus y equals a number. Then it's going to take work for us to set it up to do graphing or substitution that we could instead use to just multiply both equations if needed and eliminate. So elimination is my favorite personally, which means that when I'm choosing a method, I'm going to have to basically convince myself that elimination is not the best one to use. So elimination is kind of, for me, the catch-all. And then I'd say it's the easiest one to use if you can figure out an LCM, at least common multiple, so that you can eliminate. Okay, so I've got three problems for us to look at that I have strategically created to make us want to do each of these three methods. And really my thought process on this is going to kind of go, should we graph? Yes or no? If it's no, then should we substitute? Yes or no? If that's a no, then we'll eliminate. So it's kind of a process of elimination. Let's see here. Example 1, choose a method and solve a linear system. On each of these, I have a graph just in case we decide to graph it. Some of them really won't work out very well for graphing. For instance, if I tried to graph on this one, The way you can tell if graphing is going to be something that works out well or not is the number in front of y, we're going to end up dividing on the right side. So if I just think about that, 17 divided by 2 is not a whole number. That would be the y-intercept, and so that's not going to end up being a very nice y-intercept. Same with dividing the 8 over. Not going to work out super nicely. So I'd say a big no on graphing on this one. Substitution, I also don't feel strongly about. I guess I could solve the second one for x, and that would give me something that doesn't have any fractions. So I could use substitution. But I think I'm going to go with elimination because I can see that in front of y, I have 2 and 8, which I could make that 2 turn into a negative 8 so that I can eliminate. So that means I'm going to multiply the first equation by negative 4. Remember to multiply everything through. This is also a good review of the 3 methods because we're going to do one of each. So negative 4 times 3x is negative 12x. Negative 4 times 2y is negative 8y. And negative 4 times 17 is negative 68. Okay, so now we'll add these two equations together. Negative 4x minus 12x is negative 16x. And then 8y minus 8y cancels or eliminates. Negative 12 plus negative 68 is negative 80. So we're going to divide by negative 16 and get x equals 5. Now we take that and we plug it back in to either of these. I'm going to pick the first one just for funsies. I just don't like deciding, so I'm just going to pick the first one every single time, except when I don't. 3 times 5 is 15. And then I'm going to subtract 15. And divide by 2. And if you've already solved a bunch by elimination, like maybe just in this past week because that was what our lesson was on, you might be feeling pretty good about this whole process here. So 5, 1 is my answer. Let's look at another one and decide what method to use. So this is a different situation. We have a y equals 2x minus 1. So we could actually graph this one pretty easily if we're just willing to solve the first one for y. It actually will solve nicely because everything's divisible by 2. So that's an option. If you're like, I really like graphing, then you just solve this for y and be able to graph it. But because I purposely want to use one of each method just to show you, not because I have to, I'm going to use substitution on this. This is what I was talking about earlier, that one of them's already solved for a variable. So we might as well take this 2x minus 1 and put it in where y is on the first equation. Right, where's my mouse? Oh, right here. I'm going to plug in the 2x minus 1. So let's see, 6x plus 2 times 2x minus 1 equals 8. Then we're going to distribute. This one might be a little bit tougher to remember because it was our second method. It's not as recent. So you take the 2x minus 1 and you put it where y is. Then we distribute the number that's in front of y, which is 2. So 2 times 2x is 4x. 2 times negative 1 is negative 2. And then we do 6x and 4x together and get 10x. And then we add 2 to both sides and get 10x equals 10. So last step, divide both sides by 10, or just think in our head, 10 times what gives me 10? And our answer here would be 1. Now I'm going to take this and I'm going to plug it back in to the equation where it's already solved for y, because that's going to get me the answer the most quickly. So that means I'm going to do 2 times 1, which is 2, and then I'm going to minus 1. 2 minus 1 is 1, so y equals 1. So here we have the point 1, 1 for an answer. Example 3. What's the method we haven't used yet? What's the thing that maybe sticks out here for us to use? The answer to both of those is graphing. These are both in slope-intercept form, and just because it's in slope-intercept form doesn't mean we would have to graph it, but because the slopes are both fractions, we would have to do some work to use either of the other two methods, right? For elimination, we usually want it in standard form, so we'd have to work to get it into standard form. for substitution, we've got fractions here to deal with. That would make that less pleasant. Whereas if I just want to graph this, I have no work whatsoever to do other than just graphing them. So the first one starts at 4 and then goes down 3 and right 2. So remember to do a lot of points on the first line so you don't have to go back and make more points later. Then I'm going to graph y-intercept of -1 and go down 1 over 4, so they meet up right down here. And so our answer here is 4, -2. If you were writing things down for each of these examples, the least amount of writing is example 3. I'm kind of going on about this because I think graphing is the one that we forget about, because a lot of times it's just easier to eliminate or it's easier to substitute, and that's fine. Like I said, my favorite way is elimination, okay? But I do think that graphing is something that can be a handy tool to use here if it's the right circumstances. So there you go. Now we're also going to talk in this lesson about special cases. So this is kind of a lot of information. It may be that you want to take a break here and come back to this after you have a snack or a drink of water or something. I don't know. I'll wait, but only if you pause the video. Otherwise, I'm not waiting. So we, up until now, have gotten an answer for every single problem we've done. And that's because that's the case that's most interesting, is to get an answer. So what we've been getting is one solution because what we've had are 2 lines that just intersect somewhere. And that point where they intersect is our answer. But that's not the only options, because think about what happens with 2 lines. Is there any situation that we have where 2 lines maybe don't intersect? The answer to that is yes. So if I have 2 lines that have the same slope, this is going to look really, really, really nice. They have the same slope. I'm drawing a slope of up 2 over 3 for these 2 lines. Then because they're going to go up and over the same amount, and because they're a certain amount apart, they're just going to stay that amount apart the whole time. These are parallel lines. Parallel lines give us no solution, because our solution is where do they intersect, and these lines never intersect. That's the whole point, actually, of parallel lines, is they don't ever intersect. But then there's this third thing that's kind of weird, where we can actually have infinitely many solutions. And this maybe all would remind you of what happened when we were doing just regular equations, that we either got an answer, we got no solution, or we got all real numbers. This is kind of like that, but a little bit different. When we have infinitely many solutions, our third case here is that actually they just give us the same equation twice, so it ends up being just a single line that you would basically be graphing one line on top of the other, so they're intersecting at every single point that they're on. So we'd get infinitely many solutions in that case. Now what I'm going to do next is take you through some examples to show you with each of our methods, what does it look like when you get a special case? Because that can be really something that throws you off when that happens. I purposefully didn't have it happen before now because we were just focusing on the methods. Now we're going to focus on, okay, what do I do whenever these weird things happen? What does it mean? And so I encourage you to follow along with each of the 3 methods and how we get each special case and all of that. So we're going to start with graphing. And this is one that should seem fairly obvious, actually, that a special case is happening, because for both situations, our slopes have to be the same. So in this first case, we have y equals 1/2 x plus 3 and y equals 1/2 x minus 2. And so hopefully pretty quickly as we graph these, we see that, okay, whoops. We've got a slope of 1/2 here. And then we start at -2, and then we have a slope of 1/2 again. These are parallel lines, which means they never meet. And so this would be a case where we have no solution. And we could tell that if we were paying attention just from what the equations look like. They have the same slope, but they have different y-intercepts, because the difference between the 2 cases, right, is that for them to be parallel, they have the same slope but different y-intercepts. But for them to be the same line, they have the same slope and the same y-intercept. Now, you may have been thinking this all along, like, isn't it going to be kind of lame if they just give us the same equation twice? And you're right, that would be really lame. So what they do is they hide it from us by a situation like this one, where we have two different equations, but spoiler alert, they're actually going to end up being the same equation. If we're trying to graph these, we'd solve for y. And that's how it's going to become obvious to us that these are the same equation, is by solving for y. I subtract 2x over on the second one. It was easier to solve. That's why I started with that one. No other reason than that. On the first one here, we're going to subtract 6x and also divide by 3. So subtract 6x and then divide by 3. When we divide by 3, everything divides by 3. So the other one is y equals negative 2x plus 5. And then you look at this, and before even graphing, you're like, wait a second, these are the same line. One could argue pretty successfully that on either of these, there is a point where we would realize what the answer is and not have to graph it. And I agree with you on that. Like, if you're like, okay, I can tell these are the same line, so this would be infinitely many solutions. Please do make sure that you actually write your answer as either no solution or infinitely many solutions, depending on which it is. Don't just leave the two equations and expect me to, or your teacher to, read your mind that you knew what that meant, because what we're looking for as an answer is the actual no solution or infinitely many solutions. And I would prefer that you go ahead and graph it, because we are supposed to be solving this by graphing, and it just doesn't feel like you actually solved it by graphing if there's no graph. But you know, check with your teacher if your teacher's not me, and check with them on whether or not they're going to be a stickler for you graphing it or not. As I get older, I'm kind of like, whatever. So I guess that's good for you guys, even if I'm not really a fan of getting older. Anyway, let's move on. What's it going to look like for substitution here on example 5? So we don't have to use the substitution method on these for any reason other than that I specified that we're going to use substitution, because I want us to see what happens in each situation, so that if you're like, oh, I'm totally on the elimination boat, like that's my vibe, that's great. But if you, for whatever reason, randomly decide to use substitution at some point, I want you to know what the special cases look like. So we would pick something to solve for, and the easiest thing to do is to pick this y that does not have a coefficient, which is the fancy word for the number in front of our variables. It doesn't have a coefficient, so it will be the easiest thing to solve for by adding 8x to both sides. So we get y equals 8x minus 7. We're going to plug that in for y. So we're going to take this and put it right here. So negative 16x plus 2 times 8x minus 7 equals negative 8. So we're going to distribute. Now, as we do math, there are kind of two things that are important for us to know. How to do a problem and why do we do it? Or like the why behind the problem. Why does it work that way? Why do we do what we do to solve it? Those sorts of things. And so ideally you'd know both of those pieces of information. You'd know how to do it, but you'd also know the why behind it. But sometimes we're just not ready for the why behind it. So this is going to be a case, by the way, as we look at these special cases where if I'm going to explain the why this keeps happening to us, these special cases, and if that makes sense, then you'll actually be able to get to the answer faster. So the reason I'm showing the process of how we end up with special cases is for those of us, and it could be any of us, literally any of us could have this happen to us, that you're just going along, you're kind of on autopilot solving problems, and then all of a sudden you realize it's a special case. Because you can actually look at the problem at the very beginning and a lot of times realize that it is a special case, and maybe even what the exact answer is. So here's what happens for one of our special cases when we're substituting. See, as I add these like terms together, how they cancel out. And that's not something that we want to have happen when we're using substitution. It cancels out, and now I have negative 14 equals negative 8. So I ask myself, hey, does negative 14 equal negative 8? No, it doesn't. So since those aren't equal, the answer to this is no solution. What we're going to happen with our special cases is that our variable will cancel when we didn't want it to cancel, And we're either going to be left with something that's true or false. If it's false, it's no solution. If it's true, it's infinitely many solutions. What I like about special cases, even as unsatisfying as it might seem to you, is that we actually get to stop doing the problem sooner, because I don't have to keep going and try to find why. There is no solution to this. So let's look at this next one. We're going to solve the second equation for y here, because that looks easiest. So I'm going to subtract 5x on both sides. Y equals negative 5x plus 16. I'm going to put that in to the other equation, 10x plus 2 times negative 5x plus 16 equals 32. Now I'm going to distribute. So a very similar thing is going to happen here with just a slight difference. It's going to make this not be no solution. Not no solution. Infinitely many solutions. So that cancels, but now we have 32 equals 32. Is it true that 32 equals 32? Why, yes. Yes, it does. So because that's a true statement, we end up with infinitely many solutions. And what we mean by that, by the way, when we say infinitely many solutions, we mean that if we wanted to list the solutions that work for these two equations, we could do that forever, because there are infinitely many, an uncountable number of solutions. That does not mean that every single point is an answer. It means that if I look at these two lines, which are actually the same line, any point on that line is a solution. And because lines go on forever and are made up of infinitely many points, that's why we end up with infinitely many solutions. I said that there was a way to tell this from the very beginning. Let me actually do that on the next slide with elimination. Use elimination method to solve the linear system. By the way, if something's easy to use substitution on, it's as easy or easier to use elimination on. So this is also a situation where we practice these methods on easy things because you're just not ready for the harder problems where you might be forced to substitute or you might be forced to eliminate. And then all of these also have kind of other situations where we might use them in math. So that's why we go through and learn them. So on this, I said that there was a way to tell these were special cases at the very beginning. If they're special cases, they should be multiples of each other. At least the x's and y's should be. So for elimination, you should raise like a red flag pretty quickly here. That's like, okay, I can eliminate this because I can turn the x and y. For the first one, I can make those have 9s in front. Really easy. But then as soon as you realize, well, wait, it's going to put a 9 in front of both of them. That's where the special case and the issue comes in. Now, 3 times 3 is 9, 3 times 3 is 9, but 5 times 3 is not 9. That's the difference between infinitely many and no solution, right? So in this case, as I multiply this out and draw my line, go, okay, this eliminates and this eliminates. So this is a special case. We would have 0 on the left because we eliminated everything. And then that equals -6. So we ask ourselves, hey, does 0 equal -6? The answer to that is no. So our answer is no solution. And see how much faster we got to stop the problem because it was no solution? Gotta say, I'm kind of a fan. The second one, which by process of elimination is probably going to be infinitely many solutions, this is actually completely a multiple one of the other. So we could look at the second equation and say, oh, if I times by 3, but wait, if I times by 3, then everything eliminates, right? Because this is actually, one of the equations is actually a multiple of the other. So we can do -3x minus 6y equals -3. And then I'm going to mark this out and just say, okay, let me add them together. The x is canceled, the y is canceled, the 3 and the -3 cancel. So we get 0 equals 0, which is true. So it's infinitely many solutions. And that's our answer. I do want to mention, although maybe I'm too late to mention this, maybe it won't make sense since I didn't actually do it. You are not just limited to multiplying to change your equations. You could divide by the same number all the way through And if you have big numbers that you're starting off with, that is something that might help. So here on this one, they're not big numbers, but we could have said, hey, all these are things I can divide by 3, which gives me x plus 2y equals 1. And then we could use that equation instead. So just wanted to throw that out there, that if you notice in any equation, if you notice that, oh, they all have something in common, every single part of this has something in common, then we can divide by it and make our numbers smaller, which is nice. Thanks so much for watching. There was a lot here, so you might need to, take some time to digest. While you're doing that, check to see, are you subscribed to the channel? If not, subscribe. Hit the like button. Not necessarily because you like the content, but because you like me. If you don't like me, then that makes me sad, because I'm a super likable person. Maybe go and check out some of my other videos. I have some videos where I rap, which I hear people think is really cool. Or at least that's what they tell me. So, all right, well, I'll see you in the next video, hopefully. Bye.